Is title how to recognize the geodesics of metric connectors?
Thanks very much, John Mook. I'd just like to reiterate what John Keogh said this morning, that although there's 3 organisers listed, then the main organiser is sitting over there. So, and all we did is just make various suggestions, and they all implemented. It was really good. Right, so I think this remote is not working, so I'll just press the keys in the old-fashioned way. Okay, so here's the title of my talk, and if you go to the I've just moved to the Australian National University, so Google has probably found me already. And if you go to my website, you can find these slides on my website now. Okay, so I'm going to talk about work joint with various people. The main thing I'm going to discuss is this first article here. I'll just discuss a little bit of it. There's more in the article itself, but I don't want to get into too many details. So this is this article to appear in Journal Differential Geometry, with joint with Robert Bryant and Maciek Donatsky. So, however, as is usual when you start discussing these things with Robert, he says, oh, well, it was all known to the classical people. And in this particular case, it's sort of known to Liouville. This isn't the usual Liouville, this is a different Liouville, Roger Liouville. And so, if you look in this article in 1889, it apparently is sort of there, sort of. Okay, but the details are not, that's for sure. Okay, so I'm going to fill in the details. Okay, so here's the problem. So we're going to start with a metric. And most of this talk, I'm going to talk about 2-dimensional metrics, just metrics on a surface. And all of the discussion is local. Okay, very, very simple. From time to time, I'll mention what happens in higher dimensions. But basically, you just think of a 2-dimensional metric. So very easy. And but in any dimension, of course, you can associate to a metric its metric connection, or the Levi-Civita connection. And then you can go on and talk about the geodesics, for which, of course, you only need the connection, not the metric itself. And then, from the geodesics, you can just forget about these come with a parameterization, of course, from the connection. But let's forget about that and just look at the unparameterized geodesics. Okay? So this is what I want to discuss in this talk, then, is this blue arrow, which starts with a metric and gives you a collection of unparameterized geodesics, just the curves. Okay, so the question is, for example, can you get back from the collection of unparameterized curves to the metric, and so on. So here are the questions. First of all, what is lost? Maybe 2 metrics will give rise to the same collection of curves. So you probably already know that this actually happens sometimes. And then the question is, what do we obtain? So if you're given, well, what I'm going to assume is that you're given the unparameterized geodesics of some connection. That's what we're going to start with on the right-hand side. We're going to try and find a metric that goes along with it.
Is Riemannian metric or?
Okay, so first of all, yeah, so of course, yeah, that was going to be discussed on the later slide, but for a moment, yeah, any metric. So it doesn't matter about the signature. Okay, so already Pavel is talking about if you look at the flat metric in Euclidean space or the flat metric in Lorentzian space of 2 dimensions, they have the same geodesics, just the straight lines. Okay, so metric here means any non-degenerate symmetric form of any signature. Okay, and given such a form, so I'm using the classical notation here. This is how you get the Levi-Civita connection out of the metric itself. Right, so it's just this simple formula. This is either written out in local coordinates, if you like, or the thing on the right-hand side, this curly D, is not just coordinate derivative, but any flat connection. Okay, then you can think of this as some tensorial construction. But in any case, this is the familiar formula. Starting with a metric, you get some tensor. This tensor, the Christoffel symbols, gamma, A, B, D, is symmetric in A and B. And And then from that, you write down the Levitt-Civita connection itself, which is down the bottom there. Okay, so let's see. Is it working? Yes. Okay, thank you very much. Okay, so now I'm equipped with the remote control. That's good. Okay, so this is what happens explicitly. Okay, and now we have to talk about this business of how can you tell when you just look at the curves rather than the connection itself. Okay, so suppose you've got a torsion-free connection. So that's the context in which I'm going to talk about these things. So from a metric, you get a torsion-free connection. Suppose now you just have a torsion-free connection, not necessarily coming from a metric, and you look at another torsion-free connection defined like this. So here is how you differentiate a one form. So upsilon here, this strange Greek letter that, which is a capital Greek upsilon, is a one form. Okay, and this is written out, if you like, in local coordinates. So this is how you differentiate a one form phi with respect to this new connection with a hat over it in terms of the old connection and a one form upsilon. Okay, if you do this, then two things happen. First of all, you get a torsion-free connection. You can tell because the right-hand side is symmetric. And this correction term that you've put on is symmetric in A and B. So here is A and B that way round. Here is A and B the other way round. That's the sort of hallmark of a symmetric connection. So this new connection, if the original one was torsion-free, this one's torsion-free. And then also, it has the same unparameterized geodesics. Okay? But it's true the other way around as well. In other words, conversely, if you have a torsion-free connection which has the same unparameterized geodesics as your original connection, that one, then they are related by this formula in the red box here. Okay, so one way is a conceptual way of thinking, they just have the same geodesics, but this is a more operational way of saying the same thing. Okay, so I've turned it into some sort of algorithm or some sort of algebra already. Okay, so this is not difficult to prove, known a long time ago, probably to someone like Dini in around 1860, something like that. Okay, anyway, whatever. So now we've got either a geometric or an operational way of defining what it means for two connections to be projectively equivalent. It either means that they have the same geodesics as unparameterized curves, or it means they're related by this formula in the red box. Okay? So now the question is, if you start with a metric, you get a projective equivalence class of connections, or what's called a projective structure. And these questions are now, by operational, I mean everything's defined by formulae. And the question is, you start with the set of metrics, you end up with the set of projective structures. What property does this map sigma, which takes you from one to the other, have? And sigma is written out explicitly by saying it's the formula for how you get the Levitt-Civita connection from the metric on the previous slide, plus this equivalence relation. Okay, so that's the question. And usually I'll be doing this for surfaces. Okay, so first of all, sigma is not injective. Okay, so you can have two metrics which have the same collection of geodesics. And the first rather trivial thing you might do is multiply the metric by a constant. And all that happens there is that the natural parameterization of your metric, of your geodesics changes, but the geodesics themselves, of course, remain just as they were before. That's an overall choice of scales. That's a rather simple thing that might happen. But also, here's another metric written down on the unit disk. You may or may not recognize this metric. So this is a metric on the unit disk, quite explicit. And I claim that the metric, the geodesics of the metric on this, of this metric on the unit disk are still straight lines. Okay, and here's another one. Here's a metric on, well, in this case, all of R2. And this one is geodesics, also straight lines. So here are two rather different metrics which have exactly the same geodesics. And as I said, they're exactly the same geodesics as the flat metrics. These two things have as their geodesics just the straight lines. And here's a Riemannian one, Just to emphasize that I'm taking a non-degenerate symmetric form, not necessarily positive definite. Here's an indefinite one, and all of these have the same geodesics. So this is, of course, this first one here is the Beltrami metric, and I don't know there's a name for the second one. I've called it the Thales metric, after the Greek mathematician from around 600 BC, who was apparently the first one to study the central projection from the Earth to the sphere. Okay, so the reason that this one here, the reason that the metric, that this metric has as its geodesic straight lines, is because how I've found this metric is I've taken the sphere, here it is, and I've projected simply from the center of the sphere down to a tangent plane, say. And of course, the metrics on the round sphere are the great circles, which are the intersection of the sphere with a plane through the center, and that plane through the center hits the plane somewhere in a straight line. So you can tell right away just from that central projection from the sphere has this nice property that geodesics are preserved just as lines, not the parametrization, of course. So this is a very useful mapping. This is a very useful projection in map making, and apparently first studied by this guy here. So there may be some other more appropriate names to attach to it, since he probably didn't know about Riemannian geometry. Anyway, let's see. So that's examples of this mapping not being injective. There's more than one metric going to the same projective structure. But also, this thing is not surjective either. Then that's the main point of this talk. The question is, how can you tell, if someone gives you a connection, how can you tell whether it arises from a metric or not? So here's one I've just written down, fairly simple one here. And so I've explicitly given the Christoffel symbols. Okay, and this is just the partial derivatives in the plane. Okay, so here is a connection on the plane. And this one actually arises from a metric, whereas this one does not. And not only that, but not only does it not arise from a metric, but its geodesics are not going to be the geodesics of any metric either. Okay, so the question is, how can you tell what's the difference between this and this? I mean, they look very, very similar. Of course, the only constraint in writing down a general one of these things is that each of these components is symmetric in A and B. So this thing here is a symmetric matrix, and this thing here is a symmetric matrix. Okay, so symmetric matrix, symmetric matrix. So these things are defining torsion-free connections, that I claim that this one is actually a metric connection, and this one is not even projectively equivalent to a metric projection. And you can write down more complicated formulae, and it's very hard to tell. So, this is the question, is why not? We want some way of computing something that will tell us that this one is not projectively equivalent to a metric connection. So if you look at something a little bit more complicated, like this one, so perfectly straightforward formulae here, but, if someone gave you this one, then you'd be at a real loss to tell whether that was projectively equivalent to a metric connection, or in fact was a metric connection. But this one I claim is projectively equivalent to a metric connection. The reason I know that is that I made this one myself by taking a metric, working out the Christoffel symbols, and then doing some really silly projective transformation to it. And actually I've lost the file, so I can't. So I don't even know where this came from, but I'm assuring myself that that's how I got it. So I know that this is true. What I'm telling you is true. And if I didn't know, then the only way I could check, and I have done this, is to check that when you compute the invariance that this thing is supposed to have equal to 0, to see that it's projectively equivalent to a metric connection. It's actually true. So I'm not lying to you, but I don't know where it came from. I just can't remember. Anyway, let's see if these properties of sigma, being an injection, surjection, whatever, how they gel with just a naive dimension count of what is the freedom available in these various structures. Okay, I'm just going to do this on a surface. As soon as you go to 3 dimensions, this problem becomes much easier, in fact. Okay, so on a surface, that's the only really critical case. Okay, so if you just count dimensions, what do I mean by this? Let's look at the dimensions of the space of just jets of functions. Okay, so here we are starting with the value of a function, or more invariably said, so this is like the infinite jet bundle of functions. Okay, so it's comprised of, first of all, the value of the function, the value of its derivative, its first derivative, or in other words, more invariably captured by the bundle of one forms, and then there's the, if you've got a connection on the surface perhaps, or just look at it in local coordinates, then you're looking at the value of the second derivatives, third derivatives, fourth derivatives, and so on. Put all those together into a big filtered bundle, the jet bundle. And here are the ranks of the various bits involved. Okay, so functions, the 2 derivatives, the symmetrized, the collection of second derivatives like, d2f dx squared, d2f dx dy, and d2f dy squared, 3 components, 4 components for the third derivatives, and so on and so forth. Okay, so that's just what happens on functions. And now let's look at the various things which I've been talking about and see what the freedom is involved in these things. Okay, so, yes, therefore. Okay, so let me run through this. Okay, so here is k, and jk is, or jk plus 1, this is just jk plus 1 of functions, right? So this is the number of jets involved, the number of dimensions involved in the, well, if I start here, it will be the second jet of a function. Okay, so what you do is you add these numbers together. So 1, 2, 3, add those together, you get 6, right? So that 6 is 1 plus 2 plus 3. The next one you add 4, so you get 10, 15, 21, and so on. Right? So this is the number of degrees of freedom in a function when you look at it to higher and higher order. Okay, so that's, and I'm arranging this so that for k here, this is the k plus first jet. Right, now let's think about what happens if you look at the number of components of a metric. Okay, so the same thing but of metrics. So a metric is a symmetric 2 by 2 matrix, okay, in local coordinates. So it has 3 components. So this next row here is obtained by taking this first row here, which is obtained by summing these things, and multiplying by 3. All right, so 1 for each component. So 6 to 18, okay, so we can all multiply by 3. Yep, seem to have done that correctly. Okay, but however, remember there was this rather trivial thing that metrics up to constant scale definitely gave rise to the same projective structure. So let's just take that into account already and remove 1 from these numbers. Right, so this is the jets of metrics up to overall constant scale. So, okay, so this column, this row here, is obtained from this row here by subtracting 1. And let's compare that with the rank of a projective structure. So this one here, the rank of a jet of a projective structure. So how many components? Okay, so how do I get this row here? So this row here is, first of all, how many components are there in a projective structure? Okay, so there's this Christoffel symbols. So that's got 3 indices on it. It's symmetric in its lower indices. And so that's 6 components altogether. That would be just the Christoffel symbols by themselves. But up to projective freedom, remember, let's just go back a little bit and have a look at this. There we are. Look. So there we are. So in this freedom here, you're allowed to use a 1 form. So that's 2 components. So 6 minus 2, that's 4. Okay, so now let's look at this table again. So there are 4 components here. And if you're looking at jets to order, now this is k here, not k plus 1. So if you're looking at first jets here, that's 1 plus 2, that's 3 times 4. So that's where that 12 comes from. Okay, the 24 comes from 6 times 4. Right? 10 times 4 is 40, 15 times 4 is 60, and so on. So these numbers here are obtained from these numbers here by multiplying them by 4. But there's a shift by 1. Right? So when you're mapping from metrics to projective structures, there's a differentiation involved. Right? So that's the formula in getting the Christoffel symbols from the metric. There's one derivative involved. And that's why, if I want to know the kth jet of the projective structure, I need to know the k plus first jet of the metric. Right, so now we compare this with this. Right? So suppose you're looking at this mapping from metrics to projective structures, and you look at it jet by jet by jet. Okay, to start with, when k is equal to 1 here, there's 17 degrees of freedom here and only 12 things that you're supposed to be hitting, so you expect it to be surjective. And still these numbers are bigger. Right? So these numbers, the first time at which it looks like there's too much freedom in order to be able to hit is when k is equal to 5. Okay, when there's an 83-dimensional space of metrics up to scale, right, up to 6th order, and up to 5th order for projective structures, there's an 84-dimensional space that you're trying to hit. Okay, so there you expect a deficit. So you expect not to be able to hit projective structures when you look at jets at that order. But it's quite high, 5th order. Okay, so this is what we expect to happen. This is the naive dimension count. And what you expect to happen then is that this is not surjective when k is equal to 5. Okay, so you can't hit the 5th jets of projective structures. Okay, so perhaps more rigorously, what you expect is some sort of obstruction, some sort of polynomial perhaps, in the Christoffel symbols and their derivatives up to order 5, because that's when it first fails to be surjective, some polynomial in these things, which is an obstruction to metrizability. Right? So I'm writing this for the connection or the projective structure which is associated to gamma. And you're expecting a polynomial in the Christoffel symbols of any representative, right, which is invariant under choice of representative and such that its vanishing is an obstruction. Okay, and then at the next order, let's just go back to the table. At the next order, you expect a deficit of 5 here, right, and then 10. So let's just make a brief comment on those numbers. So at the next order, 5, you expect the deficit to be 5, and you already have one obstruction here, and then you'll have its 2 derivatives at the next order, at 6th order. So you expect you've already got maybe 3 invariants already coming from the one you knew about and its 2 derivatives, and so perhaps you expect 2 more invariants. And this is in fact exactly what happens. You now expect at 6th order 2 more invariants to pop out that you hadn't previously had. But then, after that, you expect that this number 6 here comes from differentiating these 1 more and taking the derivatives of these 2 extra ones, that's 1, 6 and 1, 6, and then that starts to overwhelm the dimension deficit now. The 10 is now overwhelmed by 6 plus 6. And so you might expect you've gone far enough, and generically that's the truth. Right? Now in all of these things, in order to go back, in order to know that you have enough invariants, you always need something like the Cauchy-Kowalewski theorem. Something like that. So you need to be working in the real analytic category. And in fact, in the smooth category, it's not true anymore. Okay, right, so let's see how you can... So the rest of the talk will be devoted to how you go about finding this invariant. Okay, so here's a connection. Okay, the first thing you do for any connection maybe is write down its curvature. In this particular case, just on a surface, let's just look at its Ricci curvature. Now, if this came from a metric, it would be symmetric. The Ricci curvature would be symmetric. But this is a general connection here, and the Ricci curvature is not necessarily symmetric. But under projective freedom here, remember there's this freedom here, And so you're not just trying to find a metric to describe this connection, but you're trying to find a metric which describes this projective class of connections. And so you're allowed to modify your connection by this projective freedom. And when you do that, it affects this Ricci curvature. And in fact, in particular, the skew part of the Ricci curvature is affected precisely in this way. So what you get is, in fact, the skew part of this, which is a 2 form, is actually just the exterior derivative of this 1 form here. Moreover, this the Bianchi identity, so this is some Bianchi identity on this curvature, just because it is a curvature, forces this 2 form to be closed. And so what you can do is always, without loss of generality, you can always restrict to connections here which have the property that their Ricci curvature is in fact symmetric. Right? You can just kill the skew part by using an appropriate upsilon. Right, so the fact that the Ricci curvature is not symmetric is no way an obstruction to finding a connection that describes the projective class. So anyway, we need perhaps a notation for a terminology for these connections. Let's just call them special. Okay, and that's not a silly terminology. It's not that I've just run out of words or anything. It's special because it's related to the special linear group rather than the general linear group, as we will see. Okay, so, and then here's this, the main thing, right? So what's going to happen in the rest of the talk is I'm going to write down an overdetermined system which describes when a projective structure has a metric or not, comes from a metric or not. And it's this, okay? So this theorem is essentially, this theorem is due to Liouville for surfaces, but for higher dimensions it's due to various other people. I'll put a few dots here and here and here because it keeps on being rediscovered. But this is a system of equations. This one here, the system of equations here, the trace-free part of this derivative of a symmetric form, right? If it has a solution which is generic, which is non-degenerate like that, then it turns out that this is if and only if this metric is projectively equivalent to a metric projection, metric connection. Okay, now I've written it like this, the trace-free part of, but I mean this is something completely explicit. You can take out the trace completely explicit like this. Okay, so this is a system of, well, it's a system of 4 differential equations, right? Because it's symmetric in B and C, and then there's another index A here, so that would be 6, but it's trace-free, so that's 2 conditions. So there's a system of 4 differential equations for 3 unknowns. Okay, and it's an overdetermined system of partial differential equations. In other words, generically this thing will have no solutions, it turns out. But we want to be much more explicit about this. Okay, the proof of this theorem is very easy, but it's a little bit surprising because it's not that, so this is the trick that was found by Liouville and various other people around the same time. It's not that this thing itself is going to give you the metric, it's that this thing in some sort of nonlinear combination here is going to give you the metric. Okay, and what you have to do is multiply it by its determinant. Its determinant is defined in this way, where you have to pick a volume form, and that volume form has to be a covariantly constant volume form, and that's where special connections is coming in, because this special connection has the property that that's the symmetry of the Ricci curvature ensures that the connection is flat on the space of volume forms, so you can actually find all these things. This is true in any dimension. Okay, we're back in general dimensions here, not for surfaces. Okay, now once you've got a system of partial differential equations like this, then there's a standard procedure of dealing with it called prolongation. So let me just run through that. So always it's easier to just, well, the first thing is so rather than writing the equation like this, the trace-free part of this, always in prolongation, what you do is you invent names for the derivatives that you don't already know about and try and write down all of the derivatives. Okay, so here you try and write down all of the derivatives of the thing you want to find, namely sigma. Okay, so you know that the trace-free part is equal to 0, so all you're left with is something with the trace. This is the Kronecker delta here. And this is another way of saying that the left-hand side has a 0 trace-free part. Okay, and then what you do is, it's always a good idea to just do the flat case as a warm-up. So what you do is you derive consequences of this equation, differential consequences of this equation, by differentiating more times and using the fact that partial derivatives commute. So here we have 0 equals, just imagine you're working with a flat connection here. So just 0 is equal to this, and then you rewrite this in two different ways. So this first way is just given by tracing over B and B here, this B and this B, and you read off what you get from there and you write it in here, and that's what you get. Whereas the other way around, you get something slightly different. Okay, so you make a deduction right away. So dividing by n, you deduce that this derivative here is actually pure trace. Right? So that's the only, and you can deduce no more. If you took the trace of this, you just get 0 equals 0, because the trace of the Kronecker delta here, this is all in n dimensions, is n, so you wouldn't gain any extra information. Okay, so you don't know what all of the derivatives of this are yet, but you do know that in the flat case, this is pure trace. In other words, there's one derivative you don't know, so you give it a name. Okay, so you call it rho. And then you play the same game again. You write down that the partial derivatives of mu now, mixed partial derivatives commute. Okay, and from this equation, you write down those mixed partial derivatives in two different ways, and you see that provided you're on a surface or higher dimensions, you can divide by this, and you deduce that this is equal to 0. So then you record these things. Okay, so you underline the equations which you've just derived. So this equation, and this equation. You see that what you've got now is a so-called closed system. So you've prolonged this thing into a closed system. So what you've got here is, you know all of the derivatives of all of these creatures in terms of themselves. So here you've got all of the derivatives of sigma are determined in terms of mu, all the derivatives of mu are determined in terms of something called rho, all of the derivatives of rho are determined into, well, a 0. That's it. Now when you do this when you do this in the curved case, all that happens is you've got to replace these things here by some appropriate curvature. That's all that happens. Okay, that gets a little bit complicated to do this in practice, but what you get is this. What you get is, in the curved case, all I've done here is write down the same equations here, except that you'll notice that this first equation hasn't changed at all, but the second equation here, you've picked up some curvature. You've picked up some, I'll tell you what these things are in a minute, but some tensors which are controlling how sigma feeds back into this. And here you pick up a little bit more extra stuff. So it's not 0 anymore here, but there's some tensors are involved. Okay, and here in general is what's happening. So this is in n dimensions. Okay, it's not the Riemannian curvature, but this is the curvature of your connection, and it's being broken up into various pieces. It's being broken up into a trace-free part, which is captured by this gadget called rho here. This is a capital rho, and this other piece here, which is called the Weil tensor. And then this thing here, y for Cotton-York, is a derivative of rho. Okay, so these are either just the usual curvature of a connection broken up into its various pieces, or they are derivatives of that. And they modify this connection. They modify this system. And now what you do is you interpret, this is a completely standard procedure. Okay, now what you do is you interpret this system of equations as what? What you do is you rewrite these equality signs by throwing everything on the right-hand side over onto the left-hand side and rewrite the whole array like this, and you think of the result here as a connection. Right, so now you've got a collection of tensors. So a symmetric tensor, another tensor, and a scalar. And you're defining a connection on these things by just taking the connection that you already know about and modifying it by these various curvature terms. Okay? And you get a connection on a bundle of, in surfaces, this would be rank 3. Right? This would be a symmetric form, so that's this is rank 3, 2, and 1. So altogether rank 6 for surfaces. Okay, and this procedure is very, very similar to what's called the Cartan connection. So in the 1920s, Cartan's, discussed projective structures. It's very popular at the time. And you can build a connection in a very, very similar way on a bundle called the Cartan bundle with a Cartan connection. This is like the procedure, and it's like what you get, but it isn't the Cartan connection. Okay, so the Cartan connection is given by the same formula as this, except that these yellow bits in the box here are removed. Okay, now the terminology here is just as in Yarn's talk. This is a connection on a vector bundle, so-called tractor bundle, tractor connection. What it is it's almost an induced connection from the Cartan connection. That's what you would get if you omitted these bits in the yellow box here. But actually, these bits in the yellow box are there. It's actually a projectively invariant modification of the Cartan connection of projective structures. That's what it is. Okay, now once you've got this thing, what do you do with it? So it's always a good idea, once you've got this thing, it's really good because you can look at its holonomy, its curvature, and stuff like that, which is, of course, what you do next. And but first of all, let's just specialize to the case of surfaces. So I just wrote out the general case just because you can, but for surfaces, actually, this file curvature is actually equal to 0. So what happens for surfaces, it's just like in the conformal case for three-dimensional things in conformal case, the Weyl curvature goes away, and you're just left with this Cotton-York tensor, and actually, so you're just left with this this row tensor, sometimes called the Schouten tensor, and then this thing here, it's the derivative of this, which controls the geometry, really. This is the first invariant that you come across. So in this formula here, this goes away, and this n becomes 2, and you end up with a slightly simpler formula. Okay, so you end up with one less term, and that has become a 2 there. Right, so as I say, perhaps you should look at the curvature of this connection now. All right, so let's do that. Let's compute its curvature. Okay, easy to do. And you find its curvature is almost 0. If its curvature were equal to 0, we'd be in trouble now. There'd be a contradiction in mathematics, because if the curvature were 0, then there'd be no problem in finding covariant constant sections here. And what you're looking for when you prolong the original equation, that's what you're looking for, because in prolonging this system, the set of solutions simply doesn't change. Okay, that was the whole point in prolonging this. I should have said that when I had the slide up. Let's just go back and have a look. Sorry. Okay, so in the flat case, the point is, when you start with this equation, these equations here are simply differential consequences of the original. Nothing's happened to the solutions at all. Right? And similarly in the curve case, nothing has happened to the solution space. So the solution space is maintained exactly the same. Okay, so if this were a flat connection, it would have plenty of solutions, and we know we're expecting to generically have no solutions. Okay, but it's pretty close to being 0. In fact, if you compare this with what happens with the Cartan connection, it's flatter than the Cartan connection. The Cartan connection would actually have a component here. Okay, whereas this thing, for surfaces, all its curvature is just concentrated in one slot. There's only a single scalar here, which is stopping it being flat. Okay, anyway, so now you can get some consequences. Right? So consequences of having a metric connection. Okay, so certainly if this is metrizable, then you're going to have a non-zero covariant constant section of this bundle, which I'll simply organize all of these tensors. The tensors sigma, rho, and mu into a single quantity, which I will call capital sigma. There it is. Okay? And now, if you have that, then of course you can differentiate again and look at the curvature. So differentiate again and look at the curvature, and that must be 0 too. And then you can read off from that some consequences. And the consequence is that this single scalar equation, which is telling you that the curvature has to be flat, the curvature has to annihilate this thing here, turns into a single scalar equation. So that's just, there's a single quantity also arranged with some various indices on it. It's got a scalar part, it's got a part which is a one form, and it's got a part with two symmetric indices on, which must contract into this thing to give you 0.
What was y again?
Right, so y is the Cotton-York tensor. That's part of the curvature. Sorry? Y is this Cotton-York tensor, which...
Yes, but it is a tensor with 3 indices.
No. Right, so I've turned... Right, so y used to have 3 indices, but because we're on a surface... Right, sorry, I should have said, when we're computing the curvature, right, because we're on a surface, I've picked a volume form in order to do that. Right. Okay, so it's come down to something with just one index on. Okay, so that's that. And then you can differentiate again. Right, so differentiate one more time. Okay, so you get a derivative onto this constraint that you already had. Right, so because this is covariant constant, right, when you differentiate this, it only differentiates the curvature, and you get some constraint on this. And this makes completely good sense because this quantity here is actually an element of the dual bundle, right? So just as the bundle, just as the tractor bundle here had components which were a symmetric 2 form, a 1 form, and a scalar, this is like the other way around. This is actually invariantly it's a section of the dual bundle, this thing here. Okay, and so you get a consequence like that. That's going to have to be 0 as well. You can actually compute what this is, right? So it's very, very explicit. So now you can figure out what the dual connection is. You can apply it to this particular element, and that's what you get there. Okay, and then you can do it again, right? So it's the usual thing that you differentiate till it hurts, differentiate it again. Okay, and again you conclude that there's another 3 constraints which are going to have to annihilate this particular thing. Okay, and so altogether we have the curvature, which is just a single scalar equation, the derivative of curvature, which is 2 more, and then the symmetrized derivative of curvature, which is another 3. Put these together into a 6-dimensional, six rows here, if you like, and then there's the 6 columns of this thing here. You get a 6x6 matrix. This matrix had better be singular because it's supposed to annihilate this non-zero section of your bundle. Okay, and so its determinant has to be 0. Okay, and that is, well, you can set all this up so that actually all these derivatives and so on were completely invariantly done. Okay, now you might complain that this is not an invariant derivative, and it's not, because I've differentiated something twice here. But nevertheless, you can set it up in a little bit better way, or you can say that, well, any correction here, is going to be absorbed when you take the determinant. But whatever, this thing is going to be, first of all, projectively invariant, and the way I've constructed it is that it is an obstruction to metrizability. Okay, so that's what you... It may vanish identically. Okay, so you may have found 0. Okay, so we better check that you don't get 0. Okay, we will do that in a minute. Okay, so for example, you can compute with Maple and see whether what Pavel says happens or not. You can compute this and see whether you get 0 or not. And you can compute, for example, a particular example. That would be really convincing. So you could take this one here and figure out what this is. And it's right. And Liouville, if he had Maple, would no doubt be able to do this. But but this simple thing here it gets quite complicated because I claim it's not metrizable because it has this non-vanishing primary obstruction. Okay, and so you can compute what it is, and it doesn't even fit on this slide. I had to go to a new slide. Okay, and there it is. Just for that simple example, that's what you get from this determinant. But you can see that it's not 0, so you're happy with that. You can see that it's actually not quite literally what I was saying before. It's not actually a polynomial in the... well, it's not a polynomial anyway. But it's something. What the story is, why there's this exponential in front of here, is actually that this connection here is not actually a special connection. Right? So the first thing you've got to do, the first thing you've got to have Maple do, and Maple can do this for you, is to find a nice integrating factor so that you make the Ricci curvature symmetric. That's the very first thing you do, and then it's just an algorithm from then on. It's just computing this big matrix and so on and so forth. And so that's what this exponential factor is doing in front of it, and then you just do this computation and you get that. Okay, so you can go on to compute these higher invariants, these next two invariants which occur at order 6. And in the generic case that's enough, and in the non-generic case, and you can say precisely what you mean by non-generic, you have to differentiate up to order 8, and then you're short of 1. Okay, but I won't get into that. Yeah, so now it's the end. The end. Yes, the end. Okay, so that's all I wanted to say. Thank you very much.